I'm Dimitris Palivos-Giannas from Chalmers University of Technology, and I'm going to present our paper, Lachesis, a middleware for customizing OS scheduling of stream processing queries. Streaming queries process unbounded datasets of streaming data in a continuous manner. They are constructed as directed graphs of processing units called operators connected by streams and executed by stream processing engines, or SPEs. Here, we focus on one-at-a-time SPEs, such as Apache Flink, that process individual tuples as soon as they are available, executing each operator on a dedicated user-level thread, which, as a rule, is mapped one-on-one to a kernel-level operating system thread. The operating system can schedule many threads concurrently and in parallel, within and across processes. However, the operating system is unaware of the specific performance goals of streaming applications, potentially leading to suboptimal query performance, especially when CPU resources are scarce, for instance, in edge devices. A response to this problem is custom scheduling, where a scheduler component uses runtime metrics to decide in which order and for how long operators are executed on the available processors. Existing state-of-the-art solutions for custom scheduling alter the core runtime of the SPEs to implement user-level scheduling, where each operator is manually scheduled as a user-level thread. This allows for fine-grained scheduling decisions, but integrating such schedulers into the core of the SPE brings implementation and compatibility risks, which are evident from the lack of adoption of user-level streaming schedulers in mainstream SPEs. Additionally, these schedulers miss advantages offered by the OS scheduler, such as transparent support for blocking operations and the ability to schedule operators of different SPEs homogeneously. As a response to these issues, we propose Lachesis, a middleware for streaming applications that controls the scheduling decisions without changes to the implementation of the SPEs or the queries. Lachesis keeps scheduling at the OS level and combines low-level mechanisms of the operating system and the SPE to provide high-level scheduling abstractions. Before describing Lachesis in more detail, let us go through a quick overview of streaming and scheduling. The slide shows an example streaming query. Data sources external to the SPE produce data items called tuples. These tuples enter the streaming query through ingress operators. Tuples are pushed through the query operators, possibly resulting in new tuples, and are eventually delivered as ingress tuples to ingress operators, which forward them to the user or other applications. Each operator is characterized by time-evolving metrics, such as its cost, which is the average time to process a tuple, and its selectivity, which is the average number of output tuples produced for each input tuple. To evaluate the impact of scheduling, we study query performance metrics, such as the throughput, which is the number of ingested tuples per second. In non-saturated systems, the throughput will be at least equal to the query input rate. We also measure the latency, which is the time difference between the ingestion of a tuple and the production of a result to which that tuple contributes, as well as the end-to-end latency, which is equal to the latency plus the waiting time until the tuple is ingested by the query. As mentioned before, Lachesis aims to use mechanisms of the operating system to influence the scheduling of streaming queries. Here we studied two such mechanisms offered by Linux. The nice mechanism is based on assigning a numerical value to the threads we want to control. In general, threads that have lower nice values are given more CPU time by the Linux scheduler. cgroup is a mechanism for fine-grained resource control in Linux. Threads can be assigned to cgroups, which then allow controlling specific resources, such as the relative share of CPU time, which we use in this work. Thus, cgroups complement nice and provide an additional scheduling dimension. Furthermore, nice values have an effect only relative to other nice values in the same cgroup, giving possibilities for isolation of different queries or processes. The slide shows an example of 5 threads that have been split into 2 cgroups and have been assigned custom nice values. In this example, threads in the second cgroup will get 4 times more CPU time compared to threads in the first group, because their CPU shares are 4 times higher. Inside each group, threads with lower nice values will get more CPU time compared to other threads in the same group. We can now describe the high-level goals of our proposed streaming scheduler, Lachesis. The main goal is to be able to perform customized operating system scheduling of streaming queries by using mechanisms such as NICE and cgroup to enforce custom user-defined scheduling policies. Lachesis should be general and extensible, allowing to use the same policy in different SPEs without alteration. Furthermore, Lachesis should support scheduling multiple queries, possibly optimizing different performance aspects of each of them. Additionally, Lachesis should be able to transparently schedule multiple queries even when these are deployed concurrently on different SPEs. Finally, Lachesis should work in scenarios where the query operators are distributed in multiple nodes. At this point, we can go through the high-level architecture of Lachesis. The user passes configuration parameters, such as the scheduling policies and scheduling period, through the UI component. The scheduling policies are abstract and can be applied to different SPEs and queries without alteration. To allow for such generality, Lachesis first needs to retrieve information from the running SPEs and convert such information into an SPE-agnostic format. This is made possible by the SPE drivers. These are small modules of Lachesis that act as bridges between the SPE and the internals of Lachesis, retrieving runtime information and converting it into information about queries, operators, and threads, as well as raw metric data referring to these entities. Then, the metric provider component efficiently transforms raw metrics from SPE drivers into a general format usable by the scheduling policies. With this information, each policy generates an abstract schedule that describes the operator priorities. Before it is applied, this abstract schedule must be converted into concrete scheduling instructions for a desired OS scheduling mechanism. This is handled by the translator of Lachesis, which are also general and independent of the scheduling policies. Having described the architecture of Lachesis, we switch to its evaluation. Lachesis is implemented in Java and is available as open source. We evaluated Lachesis on both low-powered or Droid devices, as well as a higher-powered server. To show the generality and extensibility of the framework, we implemented and evaluated drivers for 3 SPEs: Apache Storm, Apache Flink, and Libre. To evaluate the scheduling performance, we use 3 baselines. We always compare with the default OS scheduling, which is unaware of the goals of the streaming queries. We also compare with 2 state-of-the-art user-level streaming schedulers, Edgewise and Haren, each of which targets a specific SPE. In our evaluation, we use 4 groups of queries, 3 real-world and 1 synthetic. We evaluate 4 scheduling policies. Highest rate optimizes the average latency. First come, first serve optimizes the maximum latency. Qusize optimizes the average throughput and latency, and the random policy assigns random priorities to operators. We evaluate 2 translators, one using NICE and one using cgroups. And for our evaluation, we gradually increase the rate of the external data source, and we measure the query throughput, latency, end-to-end latency, as well as the goal targeted by the studied policy. This process is shown on the sample evaluation figure taken from the paper. In the interest of time, we only show some highlights from our evaluation results. Each row of the table represents a group of experiments studying one goal of Lachesis and indicating the highest improvement in average throughput and latency. As seen in the table, Lachesis achieves significant benefits in all experiment categories, attaining up to a 75% increase in throughput and more than 3 orders of magnitude reduction in latency. Of course, all detailed performance figures are available in the paper. Concluding the first part of this talk, we presented Lachesis, a middleware that controls the way the operating system schedules streaming queries in order to optimize for specific performance goals. Lachesis supports 3 SPEs out of the box and can be easily extended with new ones. Lachesis allows for scheduling multiple queries, distributed deployments, as well as multiple SPEs at the same time. In the second part of the presentation, we will dive deeper into some features of Lachesis. We will discuss how Lachesis enables SPE-agnostic scheduling policies. We will overview the priority enforcement mechanisms of Lachesis, and we will go through the implementation effort to extend Lachesis. Thank you for your attention. We now go into the second part of the presentation, where we dive deeper into the different components of Lachesis. Let us begin by discussing how Lachesis offers SPE-agnostic policies. In the first part, for the sake of simplicity, we considered queries as directed acyclic graphs of operators, ignoring various optimizations performed by the SPEs. In practice, the user usually declares a logical query graph of logical operators, and during deployment, the SPE transforms this graph into a physical query graph composed of physical operators. Through this transformation, the SPE can perform operator fusion, where lightweight operators are fused together, as well as operator fission, where one logical operator is assigned multiple physical operator instances that are executed in parallel. In this example query, logical operators B and C have been fused into one physical operator, whereas logical operator D has been parallelized into two physical operator instances. Each physical operator corresponds to exactly one thread, and thus physical operators are the basic unit scheduled by Lachesis. Based on the definition of physical and logical operators, we can now give a more concrete description of the scheduling and translation policies. At each invocation, a scheduling policy takes a set of metrics as input and produces a schedule in the form of priorities of the threads of the physical operators, as shown in the example. The translation policy converts that schedule to low-level commands that are passed to the chosen operating system scheduling mechanism. If the user knows the exact structure of the physical query graph, Lachesis allows her to write a direct policy implementation like the one shown before. However, notice that such an implementation can limit the generality of the policy. What happens, for example, if the user later changes the configuration of the SPE or runs the query in a different SPE? If that leads to a different physical query graph, then the policy itself will need to be altered. To ensure the generality of the scheduling policies, Lachesis allows also for modular two-stage scheduling policy implementations. In that case, the user can define a high-level scheduling policy that produces a logical schedule containing the priorities of the logical operators. This logical schedule is then converted to a physical one using a transformation rule. For instance, such a rule could set the priority of fused physical operators as the sum of the priorities of the logical operators that comprise them. This implementation paradigm allows Lachesis to reuse both the high-level policies as well as the transformation rules. Now we turn our attention to the metric system of Lachesis, and more specifically, the functionality that allows Lachesis to have SPE-agnostic metrics and thus SPE-agnostic scheduling policies. To begin with, each metric in Lachesis can optionally declare its dependency on other metrics, as well as a function to compute its value using these dependencies. The exact dependencies and the function are based on the metric semantics. This dependency mechanism means that each metric of Lachesis is associated with a directed acyclic metric dependency graph. Different SPEs expose different metrics and thus have different parts of the metric dependency graph available. This is known to Lachesis through information provided by the SPE drivers. The figure at the bottom shows an example graph for the main metric of the highest rate policy. Green rectangles are metrics available from the SPE driver. The metric provider of Lachesis is responsible for hiding all this complexity from the policies. More specifically, when a scheduling policy requests the highest rate metric, the metric provider will deduce that the metric is not directly available and will start traversing the dependency graph. As shown in the animation, the metric provider searches for available metrics in the dependency graph. It fetches those available metrics and uses them to compute the values of the parent metrics until the requested metric has been computed. During that process, the metric provider uses smart caching to ensure that each metric value is only fetched once from the SPE at each scheduling period. Now let's switch our attention to the enforcement of policy priorities. Priority enforcement is done using the translators. In the current implementation, there are two kinds of scheduling policies and two kinds of translators that correspond to the two kinds of operating system scheduling mechanisms used by Lachesis. The first is the single priority translators, which, as their name implies, assign a single numerical priority to each scheduled thread, using, for example, the NICE mechanism. The second is the grouping translators, which assign threads to groups, with each group being given a numerical priority. Grouping translators are used in conjunction with C groups. An important issue that translators face is that of priority normalization. More specifically, each OS mechanism usually expects priorities to be discrete and in a specific range. For example, integers from -20 to +19 for NICE. However, we want the scheduling policies of Lachesis to be decoupled from specific scheduling mechanism. So as a rule, policies are allowed to return any real number as a scheduling priority. It is thus the job of the translator to normalize the priorities of the policy to the correct numerical type and range. This is achieved by a user-configurable normalization function provided with the translator. The normalization function can be as simple as min-max normalization or more complex in case, for example, the developer wants to take advantage of the inner workings of a specific OS mechanism. Before we conclude, we will briefly discuss the extensibility of Lachesis and some additional evaluation results. As we mentioned previously, Lachesis already supports 3 SPs and 4 scheduling policies and can be easily extended with more. Here we present the effort to develop various components of Lachesis in terms of lines of code. As seen in the slide, the SP drivers we developed required from 220 to 350 lines of code, whereas the policies required from 1 to 150 lines of code. This illustrates that experienced SP users can extend Lachesis to support new SPs and new policies. Notice that such extensions do not necessitate any changes to the SPs or the streaming queries. Lastly, we briefly turn our attention back to the evaluation. In the first part of the presentation, we showed some highlights about the average throughput and latency improvements achieved by Lachesis. The figure here shows the whole latency distributions for a sample of the evaluated queries as letter value plots. The horizontal axis is the input rate in tuplets per second, and the vertical axis is the latency in seconds. The midline of each letter value plot is the median of the distribution, and each consequent box corresponds to a letter value, representing 25% of the data, then 12.5% of the data, and so forth. As shown in the figure, Lachesis not only improves the average latency, but also the whole latency distribution, achieving up to 358 times lower 99 percentile latency and 215 times lower 99.9 percentile latency compared to the default operating system scheduling. With that, we conclude the presentation of Lachesis, a middleware for customizing OS scheduling of stream processing queries. Thank you for watching.